हार्मोनिक फंक्शंस की इम्पोर्टेंट एक और प्रॉपर्टी हमें डिस्कस करनी है आज, टाइटल्ड एज मैक्सिमम प्रिंसिपल। बट उसके लिए हमें सबसे पहले हार्मोनिक फंक्शंस की मीन वैल्यू प्रॉपर्टी को डिस्कस करना होगा। What is a mean value property, by the way, of any harmonic any function? Well, let me first define it. We say that a continuous function h on a domain, it's a continuous function of two variables on a domain D, satisfies the mean value property if for each point in this domain D there exists a number, positive number, such that the average of this function over the circle of radius r, this is the average where I'm taking r to be any number lying between 0 and epsilon, and if this average over this circle is equal to value of the function at center, then we say that this function satisfies the mean value property. You have the circle here, and there you must first get some bigger circle of radius epsilon. Then it says that whatever radius, smaller radius you take than epsilon, then the average of this function over that circle has to be equal to value of the function at center. And any function satisfying this property, where average on the circle is equal to value at the center, we say that this function satisfies the mean value property. And harmonic functions are kind of functions which satisfy mean value property. Indeed, we will see later on that they are the only functions which satisfy our mean value property. The first thing that we will prove, it's one part, is that harmonic functions satisfy the mean value property on the domain wherever they are harmonic. So let me begin. Let us choose, let h be a harmonic function, on some domain D, and let us take a point in T, and since it's a domain and Z naught is its interior point, so we can choose a disk of some radius, let that radius be epsilon, such that this disk is again inside domain D. This is the definition of openness of a domain D, that every point is an interior point. Now, Uh, you know that disk is a simply connected domain. D is simply connected. It is a simply connected. So, and harmonic function and simply connected domain has a harmonic conjugate. So, what I'm going to write in brief is that there exists a harmonic function. Exists a harmonic function. There exists a harmonic function. Let us that function be denoted by k on this simply connected domain disk, such that this harmonic function is the harmonic conjugate of h, and if it is harmonic conjugate of h, then that means that this function I h plus I k, let this function be f, then this has to be analytic on this domain, this disk z naught, because k is harmonic conjugate. Now, f is an analytic function, and now I'm going to get back to Cauchy integral formula. So, by Cauchy integral formula, Cauchy integral formula, uh, what you have, you know, the value of the function inside the domain, but in particular value at the z naught has to be 1 upon 2 pi I integral over this circle. I'm taking this curve to be circle of radius r, f of z upon z minus z naught dz. This is the Cauchy integral formula, where r is any number which is less than epsilon, so that you have disk uh, of radius epsilon, and I'm choosing r to be some number which is less than epsilon, so that this disk of radius r lies strictly inside this given disk, where this function is analytic on this circle and inside it. Now what you have to do this in formula, you have to uh, change this equation to the polar form. In polar form, what you can write in polar form, you may write z minus z naught equals to r e I theta, so that dz will be equal to I times r e I theta. Then with this substitution in this Cauchy integral formula, I will have value of the function at z naught to be equal to 1 upon 2 pi I integral r is a fix, r is a center, r is a radius, and then our circle, where is it? Where is the theta? And theta varies from 0 to 2 pi, and f of z has to be then z naught plus rei theta. Z minus z naught is uh, rei theta, and dz is I times rei theta d theta. Now you see you have rei theta and rei theta get cancelled out, pi also cancels, and you are left only with this fz equals to 1 upon 2 pi. You have 0 to 2 pi f of z naught plus rei theta. And what is f? You have f to be equal to h plus ik. And if I use this decomposition of f in this above formula, and then comparing the real parts, and then using let us denote this equation by star, using an star, and then comparing the real parts, comparing the real parts, what you will have, I will have on the real part on the left hand side will be h of z naught, and on the right hand side it will be 1 upon 2 pi integral 0 to 2 pi, it is h of z naught plus r e I theta, and this is nothing but this is the value of the function, harmonic function h at z naught is equal to the mean, or what you say, the average of the value on the circle of radius r, and r can be any number lying between this. Hence, this shows that h satisfies the mean value property. Is it okay? This is a repetition kind of, you have done it in your previous work also. Is it okay? Is it clear to you that okay, now comes the maximum principle. And maximum principle in nutshell, to say what is the maximum principle harmonic function is to say that harmonic function on a bounded domain will attain its maximum always on the boundary of the domain. It cannot attain its maximum value inside in the interior of the domain. So I'm going to give you two statements. The first is a strict maximum principle. Maximum principle strict maximum principle, and this is a real version. This will be stated for a function which is real valued. And what it states that let u be a real valued harmonic function, on a domain D, such that this function is bounded by some number m on whole of the domain D. Now it says that if there is a point in D such that at that point this function attains this value maximum, if there is a certain point where this function attains its maximum value, then that function must reduce to the constant. Then uz has to be constant m for all z in D. This is the strict maximum principle. That whenever there is a point where it attains its maximum, that function is a constant. That the non-constant harmonic function will never attain this m at any point inside the domain D if m is a maximum value. And the idea of the proof is completely topological, that it will make the use of this mean value property, and why it is a topological. And the proof is, to first we are going to construct a set of all those points from the domain D over which this harmonic function u takes the value m. Now clearly, since Z0 is a one such point which belongs to domain G by hypothesis, this is a set G, so this G is a non-empty set. Our idea is to establish that this G is a closed as well as an open set, so that it becomes a open subset of a connected set D. And this connectedness argument will imply that G is either empty or it is or it is whole of the domain D. But since it is non-empty, so it will be whole of domain D. And if it is whole of domain D, that will imply that uz is equal to m for each z in domain D. So that's it. That's what we have to prove. So first I'm going to establish that this is an open set. To establish that it is an open, I have to show that each of its point is an interior point, and for that let us choose a point z1 in G. Now z1 is in G, and so z1 is in domain D also, and u is harmonic there, so u has a mean value property. So since u is harmonic and it has mean value property, so there is some epsilon positive number such that where the value of this function u at z1 is the average over this circle of radius r. ठीक है, for every, this is d theta, this is true for every 0 less than equal to r less than epsilon. So let us play with this equation now. uh, what I'm going to write, I can write left hand side as 1 upon 2 pi integral since uz1 is constant for the time being and there is no issue in writing it to be in the integral form 0 to 2 pi, and I will bring this, I'll bring this, just a minute, this right hand side to the left hand side as well, and this will give me 1 upon 2 pi integral 0 to 2 pi u z1 plus rei theta d theta, and on right hand side you will have 0. So I can write it as 0 to 2 pi 1 upon 2 pi u z1 minus u of z1 plus rei theta d theta. Now u z1 is the value m, and m is the maximum, m is the upper bound for this function, and since m being a upper bound, so u z1 being the upper bound, so this means that this number u z1 minus u z1 plus rei theta, this has to be greater than or equal to 0 for all choices of theta and r, for all choice of theta indeed by the time being, and choice of r as well. So this means that this integrand in equation first is a non-negative and continuous as well because u is a harmonic function. And you know that whenever integral of a continuous non-negative function is 0, then the function itself is 0. Hence, it implies that this has to be 0. U z1 has to be equal to u z1 plus rei theta for all theta lying between 0 and 2 pi and value of r less than epsilon. So it implies that u z1 plus r ei theta is m for all these choices of m, and that is equivalent to, so say that these points z plus r ei theta lie in domain in G for all 0 less than r less than epsilon and 0 less than equal to theta less than equal to 2 pi. That means in this disk, there's a disk center at z1 and it has a radius epsilon and all those smaller circles inside it. All these smaller circles, all possible circles inside this are part of set G. And if all these circles are part of set G, that means this whole disk must be contained inside G. So that means this implies that this whole disk with center Z1 and radius epsilon has to be in G. So now what you got? You had Z1, a point in G. You've been able to find a disk around Z1 of radius epsilon such that that disk is again inside domain G, inside this set G. This shows that this Z1 is an interior point. This is an interior point of G. And since Z1 was arbitrary point, it implies that each point of G is interior point of G That is to say that G is open. G is open set. G is open set. So G is an open set. Now we need to show that G is closed as well. To show that G is closed is equivalent to show that its complement is a open set. And what is its complement? The complement of G. G is a set where uz is equal to m. So its complement of G is this set Z in D, where uz is strictly less than m. Because uz is less than or equal to m, and we have already taken the set G where uz is equal to m. So uz strictly less than m is the complement. Now, this set is nothing but u being a real valued function. So I can write it to be this set is nothing but this is inverse image of this open interval minus infinity to m. And now this is a open set. This open interval is an open set in R. Now you have this u is a function from domain D to R, and both are topological spaces, and U is a continuous function. Harmonic functions are continuous function, and continuity says that inverse image of open set is open. So this implies that this set U inverse of minus infinity M has to be an open set, which is a complement of G. Hence, it is open, and if it is open, implies that G is closed. G is closed. So now the argument is finished that G is a open as well as closed set, and uh, D being a connectedness of D implies that you have only two possibilities: either G is empty or G is whole of domain D. Because a connected set cannot have a proper colopen subset, and so it has to be improper. And but you know that Z naught is an element which is in G, so G is non-empty. So what choice you have? You have that G is equal to D. That means G is a set where uz is equal to m, and this means that uz is equal to m for all z in D. This is the requirement, hence the proof. Is it okay?
Yes, sir.
Is it okay? So this is the real version of this harmonic functions, and there is a complex version of this maximum principle. Complex version, what it states, complex version says that suppose that u is a complex valued harmonic function. It is a complex valued harmonic function on domain D such that in complex valued it's less than or equal to, because we don't have any order in complex numbers, so there we are going to use its modulus such that its modulus is less than or equal to m for all z in D. And D is also a bounded domain. We have to be very clear here in that D needs to be a bounded domain. uz is less than or equal to m for all z in D. Okay. If u of z naught is mod of u of z naught is equal to m for some z naught in D, that means it cannot attain its modulus even. This is the modulus. If it attains its modulus, uh, maximum modulus at certain point inside domain D, then u is constant. U is a constant function. So that means non-constant harmonic function, whether it's complex valued or it's real valued, cannot attain its maximum modulus inside the domain. So let us try to do And we have this given thing that modulus of uh, u at z naught is equal to m, and we can multiply this equation with some unimodular constant. We can multiply it with some constant because it is a modulus. If I multiply it with something, what I'm going to do then, replace u by lambda u for an appropriate unimodular constant lambda such that u at z naught is equal to m. This is the thing that we want to do, so that value of u at z naught is m. This is always possible. You consider its polar form, then you can adjust the things. You will have u z naught will be equal to actually u z. This see how you can adjust things. U z naught is a complex number. It will be something, you know, its modulus is m. It will be m times e to power I theta. And if lambda I take to be e to power minus I theta, then you see that lambda times u z naught is going to be m. And this lambda is a unimodular because its modulus is 1. You will not have any. So this kind of adjustment is always possible to assume that value of u at z naught is m. So now let us take h to be real part of this u. U is a complex valued function, and let's take its real part to be h, and u is a harmonic complex valued harmonic function, and the complex valued harmonic function is the function whose real and imaginary parts both are harmonic. So this h is also harmonic function, and clearly h is harmonic, and we know that this h being a real number, so h of z is less than or equal to mod of h of z. It is less than or equal to mod of uz, because the mod of real part is always less than or equal to its the complex number, and this is less than or equal to m. And also you see that value of h, yes, someone, okay, yeah, there is somebody has to mute himself or herself. Okay, so look at this value of the h at z naught has to be m, because u at z naught is m, and m is a real number, so h at z naught has to be the real part. And so now h is a harmonic function. It is a real valued harmonic function, and it is bounded by m, but it attains this m at certain point z naught in domain D. Thus, by this maximum principle of real version of the maximum principle, this h has to be constant. By maximum principle real version, we see that this h has to be constant, and this h has to be constant m for all z in T. What it means that real part of this real part of this harmonic function u is equal to m for all z in D. But you know that mod of uz is less than or equal to m. This clearly implies that this is possible only and this is possible only if its imaginary part is 0, because you know that modulus of uz has to be real part square plus imaginary part square, but its real part square is m square and it has to be m, so this imaginary part has to be then 0. If this is 0, what it means, imaginary part is 0, its real part is constant, and hence this function u itself is a constant function, and this is done for it also. Do you have any problem? Anything?
No, sir.
So these are the strict maximum principles. One was real version and another is the complex version. And finally, as a corollary to it, we can sum up it as a maximum principle. And what this maximum principle says now for us, and it is clear from these two things that if a function is harmonic and if it is non-constant, then it will never attain its maximum inside the domain D. And how we are going to put this as let H be a complex valued harmonic function, complex valued harmonic function on a bounded domain T. Here we are taking the domain bounded such that H extends to be continuous on the boundary, extends to be continuous on the boundary of domain D, and if mod of Hz is less than or equal to m at each point in the boundary of domain D, then it says that this H is bounded by the same quantity inside the domain D also. See, I'm just writing it in brief. You have H function harmonic inside domain D, but when you combine it with its boundary, that is its closure to C, this is continuous. And this being a bounded domain means its closure is a closed and bounded, so this is a compact set. Its closure is a compact set, and you know that continuous functions and compact sets are uh, bounded functions, and they are bounded functions, hence they are bounded function, and if it is bounded implies mod of H. Mod of H is now a real valued function. It is also bounded. It is a real valued function and it is also bounded, and so it attains its maximum. It attains its maximum value. And suppose that H mod of H at Z naught is the maximum value of this function, maximum value of H Z. Then clearly this maximum value has to be less than or equal to m. This has to be less than, because this is the maximum value on boundary also. This has to be less than or equal to m. And this clearly implies that then mod of H is less than or equal to m for all Z in domain D. So this is the crux of these two strict maximum principles, that if you have a function which is bounded by some quantity on the boundary, then the same quantity is going to bound that function inside a boundary also. Do you have any questions, any query?